We often don't give a second thought to how someone is standing or sitting, but accurately recognizing these basic human postures, it's actually turning into surprisingly important technology.
Yeah, it really is. I mean, think about it. Keeping minors safe in dangerous environments, helping prevent falls for older adults.
Or even just making our computers react more naturally to us.
Exactly. And if you wanted to know someone's posture in the past, well, cameras might be the first thing that comes to mind.
Sure. Obvious choice, maybe.
But that immediately raises privacy issues, and things like bad weather or poor lighting can make those systems pretty unreliable.
And wearables, like fitness trackers.
Well, wearable devices are another option, and they can work well, yeah. But they're not always convenient, are they? And the cost can be a barrier if you need to use them widely.
Right. People have to actually wear them.
So the question becomes, is there a way to achieve this that, respects privacy, isn't affected by the environment, and doesn't require someone to wear extra gadgets?
Okay, so that brings us to radar, and a particularly interesting type called FMCW.
Yes, FMCW. Frequency modulated continuous wave millimeter-wave radar.
Millimetre-Wave. So this isn't the old radar you might be thinking of.
No, not at all. It's much more sophisticated. It can capture a wealth of information, including precise position, even subtle vibrations, and movement speed.
Wow. Okay, so it's capturing a lot. But how do we get from that raw data to actually understanding posture?
Well, that's what's fascinating, isn't it? How we can take all that raw information and actually decode it to understand specific body postures. That's really the focus of this deep dive.
Right.
We're going to explore a really insightful piece of research that looks at using machine learning, AI essentially, to analyze the point cloud data created by this FMCW millimeter wave radar to identify exactly what posture a person is in.
So sophisticated AI interpreting these subtle radar reflections.
Yeah, with impressive accuracy. It really opens doors for truly passive monitoring, without cameras or wearables.
And this research, it looked at specific postures.
It did. 6 common ones. Hands up, horse stance, like a strong athletic stance.
Right.
A lunge, lying down, simply standing and sitting. 6 distinct poses.
And the process was basically 2 stages.
That's right. First, they collected a ton of data using this radar to generate these point clouds. You can think of them as like a 3D snapshot made up of individual points where the radar reflected off the person.
A 3D map of reflections.
Exactly. Then the second stage, they used various machine learning models to see if they could correctly classify those postures based just on that point cloud data.
Okay, let's dig into that first stage then, the data collection.
Yeah.
How do they actually set things up? Where did they do this?
Well, the experiment took place in a pretty typical office space, about 3.1 by 4.9 meters, so a reasonable-sized room.
Standard office, okay.
And the radar unit itself was placed roughly in the middle of one of the longer walls, about 1 meter off the ground.
And the person?
They had one person, about 175 centimeters tall, weighing 75 kilograms, positioned around 1.5 meters away from the radar, just facing it directly. So a pretty straightforward setup, really.
Sounds simple enough. Now, you mentioned FMCW radar again. What's the specific advantage of using that kind of signal? Why not something else?
Good question. The researchers chose linear frequency modulated continuous wave radar, primarily because, well, it's relatively simple.
Okay.
The system itself isn't overly complex. The signal processing needed is fairly direct. And importantly, it's a cost-effective technology compared to some other, maybe more powerful radar systems.
Cheaper and easier to work with.
Basically, yeah. They send out these chirp signals, kind of like a rising frequency sound. And when those signals hit the person, they bounce back. The radar then processes these returning signals. It mixes them with a reference signal, amplifies them, filters out unwanted noise.
Standard signal processing steps.
Right. And this eventually gets converted into digital data that the computer can actually work with.
Okay, so we've got this stream of digital information coming from the radar. But that's not yet the 3D point cloud we need for the AI, right?
Yeah.
There are quite a few steps in between looking at their process.
Oh, yeah, absolutely. It's not quite that simple.
So walk us through that data processing pipeline. What comes first?
Okay. So the first crucial step after getting that raw digital data is something called the range fast Fourier transform, or range FFT for short. Think of this as a mathematical way to figure out how far away any reflecting objects are, based on the frequency shift in the return signal.
Okay, so it tells you distances. But what about, the desk, the chair, other stuff in the room?
Exactly. In a real-world environment like an office, you'll have things like desks and chairs that are also reflecting the radar signals, things that aren't moving. We only want to focus on the person.
Right.
That's where the moving target indication algorithm comes in, MTI.
Moving target indication. Makes sense. How does it work?
Well, the core idea here is pretty neat. Reflections from stationary objects, like furniture, will remain very consistent over time, right?
They don't move.
But reflections from a moving object, like our subject maybe shifting their weight even slightly or breathing, those reflections will change in distance, even subtly.
Okay.
So MTI essentially looks at how reflections change over a very short time frame to spot that movement. It's kind of like subtracting a still photo from a slightly later one to see only what's moved. This helps filter out the static background clutter.
So it's like the radar is saying, okay, ignore the things that aren't changing, just focus on what is. That makes a lot of sense for isolating a person.
Precisely. It cleans up the picture considerably.
What happens after that MTI step? They mention range Doppler images, RDIs.
Right. So even after filtering out the stationary objects with MTI, you can still have some interference. Sometimes radar signals bounce off multiple surfaces, say the wall, then the person, then back to the radar before returning.
Like echoes, almost.
Kind of, yeah. These are called multipath reflections, and they can muddy the waters. RDIs, range Doppler images, help to clean up this kind of noise further by looking at both range and speed information.
Okay, cleaner data again. Then they move to range angle images, or AIs.
Exactly. Following that, they create direct range angle images, or RAIs. Now, this step combines the information about the distance to the reflecting points, which we got from the FFT, with information about the angle from which those reflections are coming. And to get that angle information accurately, they use a technique called minimum variance undistorted response, or MVDR.
MVDR. That sounds pretty advanced. What's the basic idea there?
It is quite sophisticated. Imagine you have multiple radar antennas working together in an array.
Okay.
MVDR is like a really smart way of listening to all of them simultaneously and then focusing the listening power, if you will, on signals coming from a specific direction while actively tuning out signals and noise coming from other directions.
So it's like spatial filtering, pinpointing the direction.
Exactly. Think of it like using a really good directional microphone that can pick up just one person speaking clearly in a noisy, crowded room. While the math behind it, involving covariance matrices and inversions, can get complex.
Okay.
The key takeaway is that it helps the radar pinpoint the precise direction of the reflections much better than simpler methods.
So after applying MTI to filter out static objects and then MVDR to really nail down the angle, what do they get?
Well, after those steps, they can then pull out more detailed characteristics from these direct RAIs. They have a much clearer picture of where the moving points are in both range and angle.
Got it. So now we have a much clearer idea of where the radar signals are bouncing off in terms of both distance and angle, specifically from the moving person. But what about these combined RAIs they mentioned? How are they different?
Right. The direct RAIs after MTI mainly show us where there's movement. But to really understand a static posture, like someone just sitting or standing still, we also need to know the overall strength of the radar reflections from the person's body, not just the moving parts.
Okay, intensity matters too.
Definitely. So the combined RAIs are created by merging the information from the initial range FFT, which tells us how strong the reflections are at different ranges, with the refined angle information they got from using MVDR.
Bringing intensity back into the angle picture.
Exactly. And Figure 4 in the paper shows what these combined RAIs look like for the 6 different postures. They provide a much cleaner picture of the overall reflection patterns of the human body in different poses with less noise and interference.
Okay, I'm looking at Figure 4 now, and yeah, you can definitely see distinct patterns for each posture. Like the spread of reflections looks different for standing versus lying down in terms of angle and range.
Right. It starts to give you a visual signature for each posture.
So now we have these combined REIs, which are essentially these 2D images representing reflections in range and angle.
Yeah.
How do we get from that 2D map to the 3D point cloud we talked about earlier?
Good question. That's where another clever algorithm comes in called constant false alarm rate, or CFAR.
So VFAR.
Specifically, they used a 2D CAR algorithm. Think of this as a smart, adaptive way to set a threshold. It decides what counts as a real reflection from the person versus just random background noise in the REI.
How does it do that? It sounds tricky.
It looks at a small area around a specific point in the REI. These are called the training cells. It calculates the average signal strength or noise level in that surrounding area. Then it compares the signal strength at the specific point being tested to that local average. If the test point is significantly stronger than the surrounding noise floor.
It counts it as a real target point.
Exactly. It assumes it's part of the person reflecting the signal. They also use guard cells right next to the test cell to make sure a very strong signal from the target itself doesn't accidentally inflate the noise estimate and cause weaker parts of the target to be missed.
Ah, clever. So it adapts the threshold locally.
Precisely. And they do this CFRR process in two different angular planes, one for the horizontal angle, azimuth, and one for the vertical angle, elevation, using the combined REIs for each.
Okay, so that gives them potential target points in two separate 2D views. How do they merge that into 3D?
Right. To create the final 3D point cloud, they then fuse or combine these detected points from the two angular views, azimuth and elevation. They match points based on them having the same range and considering their reflection power or intensity.
So matching up the horizontal and vertical slices based on distance.
Essentially, yes. And that gives you the final 3D coordinates, x, y, z, for each point believed to belong to the person. Figure 6 in the paper shows the resulting 3D point clouds for each of the 6 postures.
Let's look at figure 6. Wow, yeah. You can really see the different shapes emerge in 3 dimensions there. Standing looks tall and thin, lying down is flat and long. You can visually distinguish them quite well.
Absolutely. You see how the points cluster differently in 3D space? That clever filtering and processing, like CFR, is really key to getting a clean picture of the person, even with background clutter. That's crucial for making this work reliably in real-world settings.
Definitely. Okay, so we've successfully gone from these raw radar signals bouncing around an office to a pretty clean 3D representation of the person inside it. Now, for the really interesting part, how do we teach a computer to look at these 3D shapes and say, ah, that's someone sitting, or that's someone doing a lunge? Let's get into their classification methodology.
Right. So the research approach for the classification part, as shown in their figure 7, basically has 3 main components after generating the point clouds.
Oh.
First, they do a bit more cleaning using object detection. Second, they extract key characteristics, or what we call features, from these cleaned point clouds.
Features, right, like measurements of the shape.
Exactly, things that describe the point cloud. And third, they feed these features into various machine learning models to see which ones can most accurately classify the posture.
Okay, let's break that down. First step in the classification stage. Object detection, using something called DBS scan. What's the purpose of that? It sounds like we already detected the object with CFRR.
That's a fair point. Even after the CFAR process, you might still have some stray, isolated points in your 3D point cloud that aren't really part of the person, just random noise that slip through. DBS scan helps clean that up.
Ah, final cleanup step.
Yeah. DBS scan stands for Density-Based Spatial Clustering of Applications with Noise. It's a pretty common algorithm for this kind of task. It's a way to group together points that are close together, packed densely in 3D space, which likely belong to the actual person, and identify any isolated points far from dense clusters as noise.
How does it decide what's dense?
It works by looking at the neighborhood around each point. It defines core points as those that have a certain minimum number of neighboring points, min-pites, within a specific distance. Points that are near a core point but aren't dense enough themselves are called border points.
And anything else?
Anything else, any point that isn't a core point or a border point, is labeled as noise and essentially discarded. They used specific values, eps equal 0.5 and min-pites equals 20 in this study. Figure 8 shows an example. You can see how it isolates the main cluster representing the person.
Okay, so it's really focusing the analysis on the main blob of points that represent the human. Makes sense. Once they have that clean, clustered 3D point cloud, they move on to feature extraction. What kind of characteristics did they pull out?
They came up with a set of 12 features, which are detailed in their table too. These features are designed to capture different aspects of the 3D point cloud's shape and also how strongly the radar signals were reflected from different parts of it.
So shape and intensity information.
Exactly. For example, they calculated the overall bounding box, essentially the length, width, and height of the point cloud cluster. Simple dimensions.
Right. How big is it in each direction?
Then they looked at the average position of all the points in the cluster, the mean x, y, and z coordinates, kind of like the center of the cloud.
Okay.
They also calculated how spread out the points were along each axis, the standard deviation in x, y, and z. This gives you an idea of the distribution or dispersion of the points.
So size, center location, and spread. That seems like a good description of the overall shape.
It does, yeah, and that makes intuitive sense for telling postures apart, right?
Right.
Someone standing will likely have a point cloud that has a much larger standard deviation in the height z dimension compared to someone who is lying down, whose spread would be greater in x and y.
Exactly. So features describing the basic dimensions and spread. But you said they also looked at reflection intensity. How do they incorporate that?
Yes, because different parts of the human body, or different clothing, might reflect radar signals with varying strength. This distribution of reflection intensity can provide additional clues about the posture that shape alone might not capture.
Interesting. So what features relate to intensity?
They calculated the center of reflection intensity in each dimension, X, Y, and Z. This is basically finding the point in 3D space where the reflections are strongest, on average. It's like a weighted average position, weighted by the intensity of each point's reflection.
Okay, so not just the geometric center, but the center of where the radar sees the most energy coming back from.
Precisely. So 12 features in total. Length, width, height, the mean coordinates, the standard deviations, and the centers of reflection intensity, capturing size, shape, position, spread, and reflection patterns.
Okay, 12 different numbers describing each 3D point cloud. But that seems like quite a few features. How do they know which ones were actually the most important for distinguishing between the 6 specific postures they were looking at? Did they use all 12?
That's a really important step feature selection. Throwing too many features, especially ones that aren't very informative, at a machine learning model can sometimes confuse it or make it less efficient.
Right, the curse of dimensionality sometimes.
Exactly. So they used another algorithm called random forest, specifically to rank how important each of those 12 features was in helping to correctly classify the different postures.
Random forest for feature ranking. How does that work?
Well, random forest is itself a type of machine learning model used for classification or regression. It works by building a whole bunch of decision trees during training. Each tree uses a random subset of the data and a random subset of the features.
Okay.
To rank feature importance, it basically looks at how much the accuracy decreases, on average across all the trees, when the values of a specific feature are randomly shuffled. If shuffling a feature messes up the accuracy a lot, it means that feature was really important.
Makes sense. So what did the ranking show? Which features popped to the top?
Figure 9 in the paper shows the results quite clearly. Based on the random forest ranking, they selected the top 6 most informative features to actually feed into their main classification models.
And which 6 were they? Let's see.
According to Figure 9, the top 6 were Feature 4, y-mean average position in the width direction. Feature 5, z-mean average position in height. Feature 6, XSD spread in the length direction. Feature 7, YC spread in width. Feature 10, YC center of reflection intensity and width. And feature 11, ZZU center of reflection intensity and height.
That's really interesting. So features related to the average height and width, the spread in length and width, and where the strongest reflections are coming from in terms of height and width, those seem like the key differentiators.
Exactly. It really highlights that characteristics related to the vertical height and horizontal width extent of the body, as well as where the radar energy is concentrated in those dimensions, are crucial for telling these specific postures apart.
What about the length dimension, how far the person extends away from the radar? Average position in X wasn't in the top 6, but the spread in XD was.
That's right. The researchers noted that in their specific experimental setup, the person was mainly facing the radar. So the average position along the length axis, x-mean, might not change as dramatically between, say, sitting and standing compared to the change in height, z-mean.
Okay.
However, the spread in the length dimension, XSD, did make it into the top 6. This suggests it still provides some valuable distinguishing information, perhaps especially for postures like hands up or lunge, which might extend further along that axis compared to just standing.
Makes sense. Okay, so now they've got their cleaned point clouds, and they've selected the 6 most powerful features to describe them. Time to see how well different machine learning algorithms can actually use these features to identify the 6 postures correctly. Which models did they pit against each other?
They tested quite a range of standard supervised machine learning algorithms. They used k-nearest neighbor, or KNN.
Okay, KNN. That one classifies based on the closest examples in the training data, right?
Exactly, based on its neighbors. Then they used Gaussian process, GP, a bit more complex probabilistic approach,
Right.
support vector machine, SVM.
SVM, yeah. Finds the best boundary between classes.
Right. Then multi-layer perceptron, MLP, which is a type of artificial neural network, often very powerful for complex patterns.
The deep learning approach, essentially.
Well, a type of neural network, yeah.
Mhm.
And they also tested naive Bayes, NB, a simpler probabilistic classifier based on Bayes' theorem. And finally, gradient boosting, GB, which builds multiple simple models sequentially to create a strong overall model. So a good mix of different techniques, from simple to more complex.
A real showdown of classification algorithms indeed. What was the setup for this machine learning part of the experiment? How much data did they use?
So they had collected a total of 600 data sets. That was 100 examples for each of the 6 postures.
Okay, balanced data.
Yes, which is good. They divided this data. 80% was used for training the models, basically teaching them to recognize the patterns associated with each posture based on those 6 features. The remaining 20% was held back as completely new, unseen data to test how well the trained models performed.
Standard train test split.
Right. And to make sure the results were reliable and not just due to a lucky split of the data, they also used a technique called 5-fold cross-validation during the training phase.
Can you remind us how cross-validation works?
Sure. With 5-fold cross-validation, you take your 80% training data and split it into 5 equal parts, or folds. Then you train the model 5 separate times. Each time, you train it on 4 of the folds and use the remaining 1 fold as a temporary validation set. You repeat this 5 times, using a different fold for validation each time. Then you average the performance across those 5 runs. It gives you a much more stable and reliable estimate of how well the model is likely to perform on new data compared to just a single train test split.
Sounds like a very thorough way to evaluate the models properly. Okay, drum roll, please. What were the main results? Which model came out on top? Who was the most accurate posture detective?
Well, looking at the accuracy results presented in Figure 10A of the paper, the multi-layer perceptron, the MLP neural network, achieved the highest accuracy.
Wow.
An impressive 94%. So it correctly identified the posture 94% of the time on the unseen test data.
Wow, that's pretty good. How did the others do?
K-nearest neighbor, KNN, and support vector machine, SVM, were very close behind, both hitting 92.5% accuracy. Gradient boosting, GB, also performed well at 92.1%.
So several models did quite well, and neither didn't.
Yeah, the Gaussian process, GP, and especially naive Bayes, NB, showed significantly lower accuracy in this particular experiment. GP was around 81% and NB was down near 70%.
Okay, so it seems like the more complex pattern recognition capabilities of MLP, or the boundary finding of SVM, or even the neighbor-based approach of KNN were better suited here than NB or GP.
That seems to be the case, yeah. The neural network in particular seems well suited for finding the subtle patterns in this kind of radar feature data.
So MLP wins on pure accuracy. They also looked at something called the kappa index, right? What does that tell us beyond just the percentage correct? Accuracy can sometimes be misleading if the data is imbalanced.
That's a great point. The kappa index, which they show in Figure 10b, is designed to address that. It's a more robust measure because it takes into account how much agreement you'd expect just by chance. So it tells you how much better the model is performing than random guessing, considering the distribution of classes. Table 3 in the paper gives a guide for interpreting kappa values ranging from poor agreement to almost perfect.
And did the kappa results tell a different story?
No, in this study, the kappa index results largely mirrored the accuracy results. MLP had the highest kappa value, indicating the most reliable classification performance even after accounting for chance agreement. And naive Bayes had the lowest kappa value by far, reinforcing that it really wasn't a good fit for this specific problem.
Okay, so MLP looks like the strongest performer overall based on both accuracy and kappa. But, overall accuracy is only part of the story, isn't it? Did the models make different kinds of mistakes? They looked at confusion matrices, right?
Exactly. The confusion matrices are really revealing. They're shown in Figure 11, one for each model. They give you a detailed breakdown of exactly how each posture was classified.
How do you read those?
The numbers along the main diagonal show the instances that were correctly classified. So for MLP, you look at the diagonal to see how many standing samples were correctly identified as standing, how many sitting as sitting, and so on.
And the numbers off the diagonal.
Those show the errors, the confusion. For example, if you look at the row for horse stance and the column for sitting in the MLP matrix, that number tells you what percentage of actual horse stance samples were mistakenly classified as sitting.
Ah, okay. So what did these matrices reveal?
Well, first, they confirmed the overall accuracy for MLP and KNN. You see generally higher numbers along the diagonal compared to, say, naive Bayes.
Right.
But they also showed some interesting patterns in the mistakes. For instance, the MLP model sometimes confused the horse stance with the sitting posture. It misclassified horse stance as sitting about 14% of the time.
Why might that be?
The researchers suggested that these two postures, horse stance and sitting, might actually produce quite similar 3D point cloud shapes in terms of their overall distribution, maybe differing mainly in the average height, zmin. So the model found them harder to tell apart.
Okay. Any other notable confusions?
KNN, which was also quite accurate overall, seemed to have a bit more trouble with the sitting posture. It sometimes mistook sitting for a horse stance about 7% of the time, or even a lunge about 4%.
Right.
Again, likely due to similarities in the point cloud features.
Interesting. Were there any postures that were easy for the models?
Yes. It's quite striking that most of the models achieved 100% accuracy or very close to it for both the lying down and the standing postures.
Totally. Perfect scores.
Pretty much, yeah. For MLP, KNN, SVM, and GB, the diagonal values for lying and standing are at or near 100%. This suggests that the radar data, the processing steps, and the chosen features did a really excellent job of capturing the unique characteristics of those two very distinct poses.
That makes sense. Lying down and standing are probably the most geometrically different from each other and from the others. Okay, so confusion matrices give us the fine-grained error details. They also looked at ROC curves and AUC. What do those add?
Right. The receiver operating characteristic curve, ROC, and the area under the curve, AUC. These are other standard ways to evaluate classification models, especially how well they can distinguish between classes.
How do they work, basically?
The ROC curve plots the true positive rate against the false positive rate at various threshold settings. Essentially, it shows the trade-off between correctly identifying a posture and incorrectly identifying it when it's not present. A curve that bows further up towards the top left corner is better.
And the AUC.
The AUC is simply the area under that ROC curve. It gives you a single number summarizing the model's ability to discriminate between classes across all thresholds. An AUC of 1 is perfect, while 0.5 is no better than random guessing.
So what did the AUC results show in Figure 12?
They showed that SVM, MLP, and gradient boosting generally performed slightly better overall, with AUC values closer to 1 for most postures compared to KNN, GP, and NB.
But were there still issues with certain postures?
Yes. The researchers pointed out that the AUC values for horse stance and sitting were, again, relatively lower compared to the other postures, even for the best models. This further reinforces the idea that those two were intrinsically harder to distinguish reliably based on the chosen radar features.
Okay, so multiple metrics are pointing to horse stance and sitting being the trickiest ones here. Let's shift gears a bit to the practical side. How long did it actually take to train these different algorithms? That can be a huge factor in real-world applications, right?
Absolutely. Training time is a very important practical consideration. If a model takes days to train, that's very different from one that trains in seconds. Figure 13 shows the training time comparison.
And what was the verdict?
As you might expect, the more complex models took longer. The MLP neural network and the gradient boosting algorithm had the longest training times.
Why is that?
Well, MLP involves iteratively adjusting many connection weights through backpropagation, which can be computationally intensive. Gradient boosting builds many trees sequentially, with each tree trying to correct the errors of the previous ones, which also takes time.
Okay, which ones were faster?
On the other end of the spectrum, K-nearest neighbor, KNN, and naive Bayes, NB, were significantly faster to train.
And why are they faster?
KNN is often called a lazy learner because most of the work is done during prediction time, not training. The training phase mainly just involves storing the training data points and their labels. Naive Bayes involves relatively simple probability calculations based on the frequencies of features, which is computationally very fast. SVM and GP were somewhere in the middle in terms of training time in this study.
So there's a clear trade-off. MLP gave the best accuracy, but it took longer to train. KNN was almost as accurate, but much faster to train.
Exactly. So the best model really depends on the specific application. If you need the absolute highest accuracy and have the computational resources and time for training, MLP might be the way to go. But if speed of training or retraining is critical, maybe KNN or SVM offer a better balance.
Definitely a key trade-off to keep in mind. Finally, the researchers presented precision, recall, and F1 scores. These are more specific metrics for each class, right? Can you quickly recap what they mean?
Sure. Precision, for a given posture like sitting, answers the question. Of all the times the model predicted sitting, how often was it actually correct? High precision means fewer false positives.
Okay. And recall.
Recall answers. Of all the actual sitting postures in the test set, how many did the model correctly identify? High recall means fewer false negatives. It didn't miss many actual sitting instances.
And F1 score.
The F1 score is the harmonic mean, a type of balanced average of precision and recall. It gives you a single number summarizing both aspects of performance for each posture. It's useful when you care about both minimizing false positives and false negatives.
Got it. So what were the key findings from Table 5, looking at these scores for each posture and model?
Well, it largely reinforces what we saw earlier. MLP generally showed high precision recall and F1 scores, particularly for lunge, sitting, and standing.
Okay.
Interestingly, KNN and SVM performed exceptionally well for the hands-up posture, achieving perfect scores, 1.0, for precision and recall in some cases.
Wow. Perfect for hands up with KN and SVM.
Yeah. And as we saw before, the lying posture was recognized really well across almost all the models' high scores nearly everywhere.
And the problem child.
And again, the horse stance consistently had lower scores, particularly lower recall for some models like MLP and NB, indicating they missed identifying it sometimes, likely due to that similarity with other postures we discussed.
Right.
So the overall conclusion from the researchers was that while MLP performed best overall in terms of raw accuracy and kappa, the optimal choice depends on the specific application's needs, balancing accuracy with training time, and maybe considering which postures are most critical to identify correctly. And it also became very clear that naive Bayes just wasn't the right tool for this job.
Okay, that makes sense. We have really gone deep into this research paper.
Yeah.
Stepping back now, what are the main takeaways from this whole exploration of using FMCW radar and machine learning for posture identification?
I think the biggest takeaway is that this combination, non-intrusive FMCW millimeter-wave radar plus modern machine learning, offers a really, really promising way to accurately identify human postures.
And it gets around the big problems with other methods.
Exactly. It neatly avoids the significant privacy issues you get with camera-based systems, and it bypasses the inconvenience and potential cost of requiring people to wear devices.
Plus the robustness.
Yes. Radar's ability to work reliably in different lighting conditions, even in darkness and through things like smoke or dust, gives it a significant practical advantage for real-world use compared to vision systems. We're seeing AI effectively learn to interpret these subtle radar reflections for genuinely passive monitoring.
And as you mentioned right at the start, the potential applications are pretty compelling. Worker safety in mines, fall prevention for older adults at home, maybe even more natural human-computer interaction.
Absolutely. The research really demonstrated the potential here. It also highlighted that important trade-off. While the more complex AI methods like MLP can achieve very high accuracy.
They take more computational horsepower.
Right. They require more resources, particularly for the training phase. So that balance between accuracy and computational cost is something anyone implementing this would need to consider carefully based on their specific needs and constraints.
Did the researchers suggest where this work could go next? Any future research directions?
They did offer a couple of suggestions based on their findings. One idea was simply to explore the performance of an even wider variety of machine learning models, perhaps some newer deep learning architectures that weren't tested here.
Okay, try more algorithms.
Another interesting avenue they proposed was to try and combine the strengths of the top performing models they identified. For example, using techniques like ensemble learning to merge the predictions of, say, MLP and KNN. The hope would be that combining different models might lead to even more robust and perhaps slightly higher accuracy overall.
Interesting. So building on this solid foundation to try and squeeze out even better performance.
Precisely.
Well, this has been a truly fascinating deep dive. Seeing how this advanced radar technology and artificial intelligence are coming together to understand something as fundamental yet complex as how we hold our bodies. It's quite amazing.
It really is pushing the boundaries of non-invasive sensing.
It definitely makes you think. I mean, given how quickly sensor technology like this millimeter-wave radar and AI are advancing, how might these kinds of posture recognition systems, seamlessly integrate into our daily lives in the future? What might that look like?
That's the big question, isn't it? The possibilities seem vast, but there are also ethical considerations to think about as this tech becomes more pervasive.
Definitely some fascinating possibilities and important questions for all of us to consider.